Okay, so this is Psych 522. It is November 5, 2020. And we're going to continue on with talking about exploratory factor analysis. So last time, you remember that we talked quite a bit about the factor analysis model. Okay, so we talked about what's up here. And I'll just get this working. Go. So we talked about this model up here, which is the factor analysis model for the exploratory factor analysis. Now, we haven't really made this distinction so far between exploratory versus confirmatory, okay? Confirmatory factor analysis. In this lecture, we're going to talk about the differences a little bit as we inch our way into structural equation modeling and path analysis. For now, the big distinction is when you're doing exploratory factor analysis, you pretty much don't have a theory as to what you're going to find. Okay, you don't know how many factors might subsume the data. So when you run the factor analysis by exploratory means, it's a little bit of a fishing expedition that you're undertaking. Now, like so many things, this distinction between confirmatory and exploratory can be broken down until it's almost meaningless, because when you do the exploratory factor analysis, as we're going to see, you have to select how many factors you would like the program to actually extract from your data. Okay, so you have to select it. So as soon as you select the number of factors, that sounds very, very much like confirmatory factor analysis. Because in confirmatory factor analysis, you have usually some kind of theory as to how many factors subsume the data. So there's a theory as the number of factors, N of factors, okay? So when you compare confirmatory to exploratory, you're going to see that the distinction disappears. And if we developed it further, it would almost literally disappear. Which one's the safer one to go by? It's usually confirmatory. Almost all statistical analysis that you ever do have some kind of a confirmatory feel to it, even if some are more exploratory than others. Okay, and that's a useful guideline to follow. It's kind of like that supervised versus unsupervised learning that we've talked about. The idea of a completely unsupervised learning is really unrealistic, because you have to start somewhere. Whenever you do a statistical model, you have to start somewhere. So usually you're on the side of some kind of supervision, if we have to use that word, of what you're modeling. Okay, and a similar distinction here. But we still will point out some of the differences between what the literature calls confirmatory versus exploratory. Okay, so last time, what were the big things about this equation? Well, the factor model equation, we said, is the observed variables in X. Okay, we're subtracting the mean, but again, that's not really important. This is the crucial thing right here. X is equal to this right here, loadings times the presumed factors plus some kind of unique variance or specific variance or some kind of disturbance term over there. What was the big distinction that we talked about between factor analysis and principal components analysis? Well, we said that in components analysis, we were actually producing a component called Z in James based on a bunch of observed variables. So A1 plus A2, these were our scalars, right? Those were our scalars, but these were observed variables. In factor analysis, we're not doing that. And that's the really, really important to understand, because we're in the Stevens text here a little bit because James doesn't cover it. And I'm going to relate back to the Mayer text. Also on the assignment, the Mayer text is going to come in handy for the final exam, rather. You'll have to do an exercise from the Mayer text for this. But in this particular chapter, you're going to be able to critically evaluate now how Stevens talks about factor analysis versus PCA. And there's a lot of confusion in the literature between the differences. So it's crucial that we pay attention to this discussion. That's the PCA. These are observed. In factor analysis, all the observed variables are here. So if you compare this to the PCA, it doesn't really have a resemblance to it because these are going to be your component scores on this side of the equal sign on the left side, whereas in the factor analysis, these are actually observed variables. So really right away, you see that they're not equal to one another, and that's really important. What about this side? Well, we said these are observed, but in the factor analysis model, these are totally unobserved, right? These are totally unobserved variables. They're latent variables, okay? Latent, unobserved variables. So right away, again, two big distinctions between EFA and PCA. Now the loadings matrix, well, that's not that different than the idea of getting scalars to weight our observed variables in PCA. So there's a bit of a similarity there. But the crucial thing is that we say that factor analysis is a linear combination of unobserved factors, whereas PCA is a combination of observed variables. So really, really important. Also, there's another element to this that we can note as well, is that in the PCA, we're not seeing an error term, right? In the PCA model, what is the PCA model? It's an eigen decomposition, right? It's an eigen decomposition. That's one way of computing the components, the eigenvalues and eigenvectors. Whereas EFA, we have this error term. So there are differences. Now, as Stevens points out in the text, citing some other sources, oftentimes they give you actually similar results. That's if you're doing the same analysis on this, requesting the same number of components or factors and you're not changing anything about it. But what we talked about last time, right? What was the other crucial thing that we talked about last time? We said that in PCA, okay, if PCA, let's say you have X1 through to X5, those are observed variables. If I run my PCA, what's PCA going to do? It's going to transform this information into components, right? It's going to transform this information into components. So how many components am I actually getting from this analysis? I'm getting C1 through C5, component 1 through component 5. That is a guarantee of PCA. Only under extraordinary circumstances will this have any conflict with it, that you actually may not be able to get the full components if your matrix is not well behaved, etc. But under 99.9% of cases, the number of variables that you subject to the PCA are the number of components you're going to get. Now, how many of these components you choose to keep from the analysis, that's a different story. So, we talked about the idea of component retention and some of the rationales for keeping one component or two, how much variance is explained, the makeup of the component, how many do you want to keep, etc. So that's a little bit of a different story. But PCA is simply transforming this information into components. EFA, okay, EFA is different in that if I start off with my X1 through X5, I'm going to run the EFA, but I'm going to have to request how many factors I'd like to extract. So when we talk about EFA, we're talking about extraction of factors. And sometimes, like in Stevens, they'll talk about it like we're extracting components as well, because Stevens will relate the two procedures, and we'll almost say they're the same, but I'll have more to say on that. But in PCA, the idea of if we're to talk about extraction at all in PCA, that would simply mean transforming to components and keeping 3 or keeping 4 or maybe even keeping 5. That's the most meaning we can get from the extraction idea here. That is not how EFA works, okay? EFA, if I take my observed variables and I extract 2 factors, okay? If I extract 2 factors, that's an entirely different idea and computation than if I extract 3 factors or 4 or 1. Why? Why did we say it's completely different? It's completely different because the loadings, right? The loadings in here, right? The loadings are going to change because these loadings are analogous to regression weights. They're analogous to regression weights and they are going to change. That does not happen here. So while this chapter does kind of relate the two and says, you know, they're kind of both almost the same thing, you have to recognize that they're not. And where that difference especially comes into play is when you do things like selecting the number of factors or selecting the number of components. And I cannot emphasize that enough, because if somebody says to you at a conference or you read in a journal article that I found a 2-factor solution, right? They say, hey, I found a 2-factor solution for IQ or whatever. That's not like saying I found a 2-component solution, because the questions you have to ask about the 2-factor solution are what? What questions do you have to ask? You have to say, well, how many factors did you extract from the procedure? Did you extract 3 and kept 2? Right? Did you extract 3 and kept 2? Or did you extract 2 and kept 2? Okay, because if I extract 3, if I tell SPSS or R, give me 3 factors, but then I decide that I'm going to keep these 2, that's different than if I never extracted this in the first place and I only extracted the first 2. Compare that to PCA, that is not the same as PCA. PCA, if I obtained 3, here I wouldn't even, I'd have to obtain 5 components, right? So it doesn't make even sense to say I'm going to extract 3 components, because it's always extracting the 5 components. I may choose to keep 3, but it's always extracting the 5. So that's how these two things are very, very different from one another. Another crucial difference, just as while we're on the topic, is you see that PCA, I can get 5 components. In factor analysis focuses on commonality between variables. PCA focuses on the variance of variables, right? Remember when we said that PCA performs the eigen transformation such to maximize the variance in the variables? Well, it's maximizing variance in variables, whereas PCA is focusing on the covariance and correlation between variables. How that materializes is that if I have x1 through x5 here, in most cases, I cannot get a 5-factor solution because it's focusing on commonality. The most I can get is a 4. Why? Because it's focusing on the commonality between variables. So that's another difference. If you try to extract 5 factors here under most models of factor analysis, and I'll talk about the exception in a second, if you try to extract 5, you're going to get an error message. It's going to say, I can't extract 5, try extracting less. And if you try to extract 5, some software might even say, are you sure you don't want to be doing this? Doing a PCA, because PCA will extract the 5 components. Now, I said there's a slight exception to this, and the exception is that some versions of EFA are actually simply transformed PCA methods. Okay, now remember I said factor analysis is like book length. It's complicated. You could easily spend your career studying factor analysis from this point on, and you'd still have a lot of work to do after. Because the idea is this, the idea is you can have a PCA, you can transform a PCA and then call it an EFA. And there's some of that in the literature, and some books will highlight that. They'll say, our first version of EFA is simply a PCA, but they're going to transform the PCA a little bit, but it still ends up being a PCA. It simply transforms the weights a little bit. And they sometimes call that the principal component version of factor analysis. And in that particular case, you can actually extract 5 factors here. because it's really what you're doing is a PCA. It's simply called an EFA because it's transformed a little bit. So you have to be aware of that as well. Let me just repeat that. Well, what I'm saying is that in most versions of factor analysis, you're only going to be able to get 4 factors here. Extracting 5 won't make sense. But there is an exception that in some versions of factor analysis, because they're transformed PCA analysis, and they call it like the principal components version of factor analysis. In those cases, you may be able to get 5. Okay, so just be aware of that. But 99% of cases, you can't go wrong with thinking of the 4 as being the maximum, because in 99.9% of cases, that's what's going to be true. Okay, so again, it's very confusing because you got factor analysis, you got principal components, and I'm going to be completely honest with you, this chapter does not help that much in clarifying that distinction, because they kind of overlap the 2 procedures, which is why as we go through it, I'm going to continuously remind us that's a PCA. That's not an EFA, what they've just done here. And otherwise, it can be really confusing because you think, you're being told that they're 2 different procedures. And then when you get into SPSS, you look under EFA and then it says, hey, do you want to do a principal components analysis? So we got to talk about that as to how software treats those things. In our software, which you'll be doing for the final exam assignment, that is going to distinguish between EFA and PCA. There's not going to be any confusion there. In SPSS, SPSS overlaps them to a great deal. So you simply need to be aware when you're using different versions of software, what you're actually looking at in the software program. Okay, and I have more to say to that as we go. Now, this equation here, just as a quick recap, what was this equation about? Well, this equation has the same thing as this one up here, only that we introduced a transformation matrix and we multiply it by its transpose. That ends up being the identity matrix. And the idea there is one of the big problems or limitations of factor analysis is that you can subject it to a transformation matrix. So I can subject these loadings to the transformation matrix T, and what was the big outcome from this? I can still get the reproduction of the covariance matrix, right? I can still get the reproduction of that covariance matrix. So remember we said that the covariance matrix is equal to those loadings plus an error matrix. I can still get this reproduction even if I subject it to a transformation matrix. Now, what was the big thing about that? Well, this chapter is going to talk about that, not by the terms we're looking at here. It's just going to mention it in verbal speech. But we're going to see that this idea of transforming by a matrix here is going to say that you can actually choose different weights. You can actually choose different weights for these things, and you'll still get a reproduction of the covariance matrix. Remember again from last time, the goal on a technical level of factor analysis is to reproduce this, right? Yeah, theory aside, what factor analysis says, try to reproduce this. You're gonna have a covariance matrix of variables, covariance or correlation matrix. There's X1, X5, X1 up to X5, and factor analysis says, try to reproduce this. And then you say, well, how am I going to reproduce this? And well, try to do it by the loadings. This is the noise, but try to do it by the loadings. So the big question of factor analysis then becomes, what's these matrices going to look like? You can just take one of them. What's this going to look like? Well, it's going to be a loading matrix, but the question is how many loadings is it going to have? Is it going to have loadings for 1 factor? Is it going to have loadings for 2? Is it going to have loadings for 3, etc.? So here's the problem with factor analysis. It's subject to a transformation matrix, which means you can produce the same covariance matrix. What that means is that these loading values, right, this loading matrix is not unique. It's not unique. Okay, it's not unique. And when we say not unique, we say, well, you can have different values for it. Uniqueness is nice, right? Uniqueness is nice because if something's unique, you can say, well, I found the solution, right? If it's unique, say, well, I found the solution, the solution. If it's not unique, well, you have to say, I found a solution, right? So imagine you're doing some kind of you're looking for a COVID vaccine, and you say, well, we found the solution. We found the vaccine. Now, you probably found a vaccine. Other vaccines would also work as well. Very similar idea. And why is this posing a problem? This poses a problem for this reason here, that nobody knows what the correct solution is. If it's not unique, then a whole bunch of different solutions can fit. And last time we talked about the problem with that, the problem is that since this contains either one factor, two factors, three factors, 4, 5, etc., nobody knows what the right solution is. Is it a one factor? Is it a two? Is it a three, etc.? So the question becomes, how are you going to know what the correct solution is? If you cannot simply establish a unique solution, the selection criteria for getting a correct solution is going to have to involve something else other than just running the factor analysis, right? So you can't just run the factor analysis. When we do techniques like regression, ANOVA, we usually do things like we say, well, run the ANOVA, right? Run the ANOVA and you get your result and you reject your null hypotheses and all the rest of it. We don't have to say, but that's only one version or that's only one possibility. We just say the ANOVA's been done, period. Now, that doesn't mean that there's not complexities that come into that with how you operationalize your variables and all those things. But we don't have to talk about this uniqueness really when we talk about ANOVA, when we talk about regression, etc. In the factor analysis we do, because those factors are right over here and the loading matrix is over here. It's on this side of the equation, so we have to talk about the uniqueness. So it's how to select those values. And as we're going to see, we're going to be able to rotate factors, and that's going to pose further complications. Okay, so that's where we're headed, and let's go. You can check this over. Talk about exploratory regression. Sometimes you have a large number of predictors, and you actually want to reduce things down a little bit. Now, usually if you want to use variables for predictors, you're usually doing a PCA if you want to reduce the variables down. But in terms of how Stevens is talking about it, because he's equating the PCA with the EFA a little bit, you're going to see that overlap of our PCA discussion, but you still have to realize they're distinct. Scale development is actually really popular for factor analysis, because when you think about scale development, remember that kind of theoretical rationale for factor analysis. You have X1, you have X2, you have X3, and then underneath, you have maybe a latent idea, right? There's your factor. Well, your factor is giving rise to the observed variable. So you can see in scale development, factor analysis is pretty popular because it kind of fits the theory, right? Saying, you're good in verbal, you're good in analytical, you're good in quantitative. What's giving rise to all these abilities? Hey, maybe it's IQ. Okay, maybe it's IQ. That's the original idea behind factor analysis. Since then, factor analysis is misused in a lot of contexts, and you don't always get this give rise to or like explains these observed variables. And oftentimes when people are talking about it not in this particular fashion, what they're really talking about is the PCA idea, where they're just trying to account variance in the variables. But this is the original and the most applicable version of factor analysis, is that latent idea, the latent variable subsuming observed correlations. So if you don't have this idea, you should consider whether doing a factor analysis is really worth doing. You don't just want to treat factor analysis as just kind of like some kind of variable that just points to other variables. Like one analysis I saw in a book once was kind of like this factor was the homework factor. And then they had like your math homework, your English homework, and stuff like that, right? They had the different variables. And the author or researcher called it the homework factor. Well, what is homework giving rise to these variables? It kind of doesn't really make sense, right? Like, how is homework a latent variable? How is homework subsuming the observed variables? Not really, right? Now, factor analysis will still fit the model, but you have to ask, does this make sense? And that's half the battle with this stuff is, what we're learning in stats and stuff like that is you always, the computer will do almost anything you want it to do. Does this make methodological sense? Does it make research sense to be doing this? Otherwise, you can do it, but it's going to come under criticism by saying, why would you think this is a factor? So you have to think about that. The other idea too, as we proceed, we're going to see in the chapter, is how do you name this factor? Okay, this factor does not necessarily have a name, and that's important. So when we see some of the factors that Stevens comes up with, we're going to critically evaluate, how do we even know that factor exists? And the truth of the matter is we're going to have zero evidence. We're going to have zero evidence that IQ exists here. We're going to have zero evidence for it. Why are we calling it IQ is going to be more of research convention, the zeitgeist that we find ourselves in, of how we choose to conceptualize of this information. And if you think that's a simple matter, it's not, because if you look at this stuff historically a little bit, you're going to find out that some variables are actually going to be the same thing as other variables. We just call them different names. So, before you do any kind of factor analysis or consider these things, you should think about those things too. Before you name a factor, you should ask yourself, has this been found 10 years ago, but we're just naming it something different? And there's a lot of stuff in the literature like that people are doing the same research on supposedly different variables that actually mean the same thing or are very, very closely allied in terms of a Venn diagram. And so you have to wonder, are we just, when we analyze different variables, are we just playing with semantics? And one thing that comes to mind is when you think of like mindfulness research, you want to be critical of those things, right? You say, wait, what is mindfulness? Has mindfulness gone under, let me just write down, there's mindfulness. Has mindfulness been subsumed under a different name before, for which everything's been analyzed on that variable? Or is mindfulness, to use that unique term again, is mindfulness unique? Is there something about mindfulness that's not true about other things we've called these things before? And that's how you have to be critical as a researcher when you look at these things and say, has this been done before? What does this overlap with? Instead of pretending like just because you gave it a new name, that it's all of a sudden a new variable. Okay? And I think you'd find if you look, when you do your literature, you don't just want to go back 5 years or 10 years, go back 40, 50 years, 60 years, see what else is in there. And it may help inform how you do your research today for things like that. Okay, so we talked about scale development here. Well, it's useful in scale development. So maybe you have those 30 items. And as Stevens is pointing out, well, maybe it's not measuring 30 different constructs. So you might want to reduce the data down. And both PCA and EFA can be used for that purpose. In factor analysis, a mathematical model is set up and factor scores, you can get factor scores, we'll talk about that briefly, may be estimated, whereas in components analysis, we're simply transforming the original available into new sets of linear combinations of principal components. Okay, this is right on. This is really good, and the authors do a nice job of distinguishing there. After this distinction is made, though, you're going to see later in the chapter that it kind of PCA is treated like EFA a little bit. But if you remember this distinction, then you can interpret the rest of the chapter as we go. Okay, so here's the distinction in SPSS. We're going to start in this chapter talking about PCA really quickly. And that's the default method to extract factors in SPSS. So right here, Okay, and I'm just telling you, these distinctions are important to understand what PC and EFA are actually doing, because otherwise you'll get lost in it. Extract factors in factor analysis, and then you have principal components analysis here. So, without our previous discussion, you start to think that principal components extraction is the same thing as factor analysis extraction. So be mindful, to use that word again, be mindful of what we just talked about the extraction idea. Again, the person who says I've extracted 3 factors, that's not the same as saying I've extracted 3 components. It's just not the same. And if somebody says I found a 2-factor solution, well, how many did you extract? That makes sense. If I found a 2-PCA, a 2-PC solution, you're not really asking how many did you extract, because it's kind of irrelevant. They've chosen a 2-PCA based on maximizing the variance, and those account for a lot of variance, presumably. But the idea of how many did you extract doesn't make sense in the PCA framework. Why? Because if you extract 2 or 3 or 4, it doesn't change the loadings. That's not true in the EFA. Extracting 2, 3, or 4 does change the loadings. These are not going to be the same depending on how many factors you extract. So really, really important. One method here in factor analysis that they'll talk about briefly is the principal axis factoring, which is one method of factor analysis. It's not the only method. There are so many methods of factor analysis that oftentimes if you have to do a quick version of factor analysis, you can do the principal axis factoring. Another one is maximum likelihood factoring. They won't necessarily give you identical results as well. So let's introduce another complexity into this that's necessary for us to understand what factor analysis is and its limitations and benefits and all that, is not only do we have these issues at work and the uniqueness of loadings compared to PCA, we have different estimation methods. Right, so even after you get past this, you say, I got it, I got the caveat, I'm good, I got the caveat. Now you have to choose a certain estimation method, and all the estimation methods will not generate the same results. So again, we're back at the conference and someone says, I found a 2-factor solution. Okay, how many did you extract? How many did you keep from the extraction? What method of estimation did you use? Why are you using this method of estimation? Would a different method of estimation have provided a different solution? Lots of questions. Notice that in PCA, it's not a problem. The PCA are going to be what the PCA are going to be. The components are going to be what the components are going to be. You don't have to ask somebody in components analysis, how many did you extract? What method of estimation did you use? Because the components, under most circumstances, are just going to be what the components are. That's why we say components analysis, relatively simple and atheoretical compared to EFA. EFA, lots of complexities. PCA, as we said, can be just computed by doing an eigenanalysis. An eigenanalysis, as we said, is just a transformation on the data. It's just like a mechanical transformation on that data that it's going to be what it's going to be. EFA, not so, not so. EFA, you got to ask questions. You got to understand where that factor analysis is coming from. Okay, so I hope that distinction is really clear because it's important. It's really important. We'll talk about confirmatory factor analysis towards the end of today as we get into SCM a little bit. So principal components method, well, here's our components, and we've seen that before in James. We've seen all of this. There's our normalization constraint, and we said we want it to be the largest eigenvalue of the sample covariance matrix. So this is PCA all over again. And we said that we're going to choose the second linear combination, uncorrelated, orthogonal. The two terms do not mean the same, but one basically implies the other in this case, that they're orthogonal. Therefore, they're going to be uncorrelated. But again, the uncorrelatedness and orthogonal, those are distinct concepts. You don't want to talk about them like they're the same. But in this particular case, you can just, you can equate them, but don't equate them in general. There's your second component. We've got the normalization constraint. We've got the correlation between y1 and y2 is 0, right? So the components keep things orthogonal, keeps the correlation between components equal to 0, maximizes the variance in the first component, uncorrelated to the second maximizes the variance in the second component, uncorrelated to the first and the third, etc. So they're providing separate productions of variance. Okay, then we talk about the loadings. Now, here again, well, we got the factor or component loadings. That's not a small distinction, right? And in the chapter, it's kind of factor or component loadings. Well, they're not quite the same. Component loadings, PCA. Factor loadings, EFA. Okay, and now that you've heard what I've had to say about PCA versus EFA earlier in the chapter, kind of prepping us up for what we're going to read here. It's a great chapter, but we got to make these distinctions a little bit more finely. Now you're better prepared to interpret this, right? You say, well, components of loadings are PCA. Factor loadings, okay, yeah, but wait, right? Those are those things. And that's a different thing because it's subject to all the things we've talked about. So you don't just want to be just kind of saying these are interchangeable words. They refer to different things. And if you're a psychologist, maybe you're not a psychologist, maybe you're something else, but you want to give a name to the factors so they might make sense to the composite variable. So naming factors is a convention in factor analysis. The factor analysis mechanics do not know anything about naming variables. And what I mean by that is it's doing the factor analysis. It can't name them for you. It doesn't even know what that means, right? The math doesn't know what's going on. The math just knows it's doing what it's doing. So subjective component here that we need to talk about, but you may wish to give them names. On a rigorous level, there's problems with that, and we'll talk about that, okay? The signs of the coefficients might be of interest, okay? Not only the size of the loadings, but you might want to look at the sign. Sometimes you're going to have positive, you're going to have negative, and that could be actually indicating that you're having contrasting factors or abilities and things like that, which we'll talk about. Okay. Whether you're doing a components analysis or factor analysis from a correlation or covariance matrix are not the same. We saw that in PCA and James. We said they're not the same. Well, that also holds over in factor analysis. They're not the same. So you have to be able to choose that matrix and maybe even run it under both solutions. We talked about in PCA, doing it on the correlation matrix, especially if you have wildly different variances of your variables, might be a good idea. And we saw that with the biplot in PCA. Well, a similar idea is going to hold in EFA, that especially if your variables have wildly different variances and they're different scales, especially you want to just run it on the correlation. EFA, if you want a generalization here, EFA is generally a correlation type thing that you're going to do on the correlation matrix. Whereas, first and foremost, PCA, you want to think of the covariance matrix. Doesn't mean you're not going to do the PCA eventually on the correlation, but PCA is more in the tradition of covariance matrix, whereas EFA is a little bit more towards correlation matrix. That's a useful way to distinguish the two. But don't hold hard to that and say PCA has to be done on covariance matrix, because it doesn't. But the spirit of these techniques is PCA is associated more with the covariance. Now, we're also going to look at a test here that you can obtain in R and SPSS called the Bartlett sphericity test. Now, there's details in this that the book doesn't present, so we're not going to be looking at the formula or anything like that. But this tests the null hypothesis that the variables in the population correlation matrix are uncorrelated. What that really amounts to is evaluating the null that the correlation matrix is an identity matrix. What's an identity matrix? One along the main diagonal, zeros everywhere else, right? There's my correlation matrix. Now, why might this test be useful at sometimes. It may be useful because if you're analyzing a matrix like this, if this is what your true correlation matrix looks like, then doing an EFA is not a good idea. It's not going to tell you anything. There's no correlation between variables. There's X1 and there's X2 in a 2-variable problem. So what Bartlett's comes around and says, here, evaluate that null hypothesis. If the HO is that it's uncorrelated, which means it's an identity matrix, then we want to reject this, right? We want to reject HO, because if you can reject HO, then that suggests it's not an identity matrix. And if it's not an identity matrix, it suggests that you have sufficient correlation between variables, making doing the factor analysis worthwhile. Okay, that's the idea behind that test. Now, you don't have to do that test. That test is going to be sensitive to assumptions as well, but it's a good kind of guideline to look at it. What's Bartlett's test telling us? And you can use that in your write-ups as well. At the same time, nothing should prevent you from doing the factor analysis if you really want to do it. So sometimes people look at Bartlett's, they say, oh my goodness, I didn't pass Bartlett's test. And it's like a huge panic, right? It's like, oh my God, I couldn't reject the null hypothesis for Bartlett's. Well, try the factor analysis anyway, see what happens. You're not going to break the computer. So it's not like you have to pass this in order to do the FA, but it's a useful test to do it to give you an idea of that correlation. Or you can also look at correlation matrices to see how much correlation you have, but the Bartlett's is kind of nice to do. How many factors to extract? Criteria for it, it's entirely subjective. There are no true criteria. Now there's stuff that the book talks about here a little bit, such as having eigenvalues greater than 1, okay, greater than 1, because if you're analyzing a correlation matrix, then as we're going to see, that is kind of like an average eigenvalue. So extracting with eigenvalues greater than 1 is sometimes a criterion used, but really all of these are just kind of loose guidelines that you can look at. The ultimate decision is going to be yours in terms of what you want to extract. But we'll look at the eigen criterion a little bit as we go. We'll talk about communalities in a second here. We'll talk about the Scree test, which just lists the eigenvalues, the magnitudes of them, and it plots them against their numbers. So we'll look at a Scree plot. Scree plots really don't tell you that much. It just tells you the size of the eigenvalues in a graph. Scree tests were a lot more useful historically when we didn't have computers and stuff like that, that you actually wanted to plot things out and say, look, this one is accounting for, there's the variance, is accounting for a lot more variance than the others. So you said, well, maybe I'm going to choose a 1-factor solution, because these here, it kind of seems like they're about equal and they're like less than 1. Maybe there's 1, so these are less than 1. But again, the output is going to tell you pretty much the same thing, that interpreting the Scree plot is really, there's nothing special about interpreting it. Even the book calls it a Scree test, which is a little bit much. It's not really a Scree test, it's just a plot of eigenvalues. Okay, we'll talk about parallel analysis in a moment after the break, and parallel analysis will also be something that's talked about in MAIR too. So it'll be a little bit of something that you have to do for the final exam as well. And this is another method. It's based on a bootstrap method that's going to help you decide on the number of factors. Okay, but again, it's not always going to be that useful, so we have to be able to put it in context. We'll talk about it. Statistical significance for the number of factors is usually not computed because it's really not a statistical significance type of thing when you're doing factor analysis. And that's where, when you're doing like exploratory, the EFA, you're not looking at statistical significance. Now, there's some computer output in R that will produce a test of fit for the number of factors, and that we'll look at when we look at confirmatory factor analysis a little bit. But when you do the typical EFA, you're not looking anywhere for statistical significance of the number of factors. That's just not how the procedure works. If you're basing the number of factors based on some kind of a test that the software is telling you is the optimal number of factors, That is insufficient criteria. Okay, that's insufficient criteria. It may be useful at sometimes, but you definitely want to keep the retention of factors to be something research-based. How many factors account for a specific amount of total variance? Well, you can use that as well, but again, if you're explaining 50% of the variance and you have a meaningful factor solution, maybe that's what you want. Maybe that's going to be good enough. In another case, maybe you're explaining 70% of the variance, but you don't have a meaningful factor solution and you're keeping 6 or 7 factors. Then it makes no sense to even be doing this. So again, you don't want to get in the cookbook habit of following these certain rules. These are guidelines only. The biggest thing is the factor meaningfulness. Not only is it important, it's almost the most important thing, because if your factor solution isn't meaningful, then that stuff is just like out the window in terms of this. Doesn't mean you can't hold on to it and put it in your desk drawer and hang on to it. It just means that if you can't make any sense of the factors, then really what do you have? So this should actually be number one. Whenever somebody does a factor analysis, if you know the area really well, you should start to see factors come out. If you can't, you don't want to be making up things too, right? And that's the thing between theory and evidence, right? Theory and evidence. If it's not jumping out at you, then you don't want to make up an ad hoc explanation for it. Because anybody can make up ad hoc explanations, right? Anybody can explain anything after the case. So you don't want to be, any theory fits the data after you look at it. It's the theory that you have before the data is analyzed that's most meaningful. At minimum, cross-validation, right? You can say, you know what, I've pulled out 2 factors. Here's my theory that black holes don't exist. Well, okay, can you actually duplicate that? That's a silly example, but you get the idea, is that if you have a theory after the case, then at least do cross-validation. Otherwise, your theory is meaningless. Right. Why did the dog want to go outside today? Well, he wanted to go outside because he, felt an electromagnetic pattern in the skies that was attracting him outside. Wow, that's a theory that explains the dog's behavior only if I cross-validate it, preferably doing some kind of an experiment. Otherwise, the explanation just kind of is meaningless. Okay, so the idea of rotation of factors is something we're going to talk about. I'm going to take a quick break. Come back, we'll talk about the rotation idea. Now, this relates to, in Stevens here, the idea of subjecting things to a transformation matrix that we've talked about in our previous notes and just above. So remember we said that factor solutions are not unique. Well, in part, what this means is that they can be subjected to a rotation. And you can subject them to a rotation and you can still reproduce this just fine. So when you subject it to a transformation matrix, which is implying, in this case, a rotation, not all transformation matrices are rotations, but in the case of factor analysis, the transformation that we're actually subjecting it to is a rotation. So there's a distinction there, right? You don't want to associate rotations, transformation matrix, rotation. What you do want to associate is that in this particular case, the transformation matrix is going to be a rotation matrix for which you rotate your solution, but you can still produce this just as well. So the question is going to become, what's the right rotation? Out of many different rotations, which is the right one, or is the original solution the best? So we'll take a quick break and we will continue talking about those issues. Be right back.